Let us discuss the number e. So what is the definition of the number e? The definition we are going to work with is that e is the series 1 over n factorial, n from 0 to infinity. Here, remember, n factorial is the product of all the integers that are equal than n all the way to 1. And by convention, we take 1 factorial equal to 1 and 0 factorial equal to 1 too. Okay, the last one is by definition. Now, this series, we are certain that it converges. Okay, because we know it's bounded. This we can show easily. So this series, when we look at Sn, well, actually I said this, the series is bounded, Sn is bounded. Okay, how do we see that? Sn is 1 plus 1 plus 1 divided by 2 factorial, 1 divided by 3 factorial, and so on, up to 1 over n factorial. But then here, notice what happens. Here we have 1 times 2 times 3, 1 times 2 times 3, all the way to n, okay? Here, we can get something larger if we divide by something smaller. Okay, so what is the smallest we can do? With 1 plus 1 plus 1/2 plus 1 divided by 2 to the power 2 plus 1 divided by 2 to the power n minus 1. So here we are replacing all the numbers that are not 2 by 2 itself. Okay, and notice here, because the 1 doesn't really do anything, we are just going to get n minus 1 number 2's. Okay, so we have 2, 2, 2, and so on. We get this estimate that is actually an estimate by a geometric series. Okay, so this geometric series is going to be less than, so we have 1 plus the whole thing. We can estimate it by 3. Okay, you can do the precise computation if you want. Okay, this is less than the sum of the whole series. Be my guest. Okay, now we know it's bounded, and we also know that Sn it's a non-decreasing, it's monotone, let's say it that way. Okay, because all the terms are non-negative, so then the two together, we know that it converges. Okay, so once we know it converges, whatever the limit is, we call it E. Okay, but there is another way that we may have seen that the number E is defined. Instead of using a series, it uses a limit of a sequence. The limit of 1 plus 1 over n to the power n as n goes to infinity is actually E. Okay, sometimes this is taken as a definition, but because we have defined the number E in a different way, okay, as the sum of 1 over n factorial n equals 0 to infinity, this is something that now we need to prove. Okay, we cannot define it in two different ways. Well, actually we can, but if we do, we need to show the two things are equivalent. They define the same object. Okay, so how are we doing to define this? Let us take the partial sums, okay, from 0 to n of 1 over k factorial, and let me call Tn the general term of the sequence 1 plus 1 over n to the power n. And let us compare Sn and Tn. Okay, here there is a bit of a manipulation. We take Tn, 1 plus 1 over n to the power n. Okay, and here what we are going to use is the binomial theorem. 1 plus x to the power n, okay, is the sum, let's say from k equal 0 to n of, well, is 1 to a power times x to the other power, so we don't have to write the 1. We just need to write x to the power k, and then we have the combinatorial numbers n over k. These are defined as n factorial divided by k factorial n minus k factorial, but we know this. Okay, here there's a bit of a trick that we are going to need, so let me write it carefully. The book kind of goes over these steps, so it's a bit more difficult to grasp. So n divided by k factorial n minus k factorial, this is what we just said. So this is equivalent to n times n minus 1 times n minus 2 and so on. We will stop at n minus k plus 1. Okay, because then the next one is n minus k factorial that we can just cancel out. Let me actually do that, n minus k factorial, and then here we have k factorial, n minus k factorial, and these two cancel. Okay, but once we have this, we can factor the n in each of the terms in the numerator. So we can have n to the power k. And here the first one is obviously absorbed. So this is 1 minus, looking at this is 1 minus 1 over n, and so on, 1 minus k minus 1 divided by n. Okay, and here we still divide by k factorial. All right, so let's use this formula, the two formulas. Here x is 1 over n, so we have the sum as k equals 0 to n over k, 1 over n to the power k. All right, and then I apply the second formula, sum k equals 0 to infinity, to n of this thing here that I'll just copy paste. I'll put it here. There we go. And then the 1 over k, that 1 over n to the power k that I still had. Okay, now this is everything all right, but now notice there is a cancellation. The n over k's cancel out. Okay, and what we have, let me write it carefully. Let me write it in extended form. So what we are going to have, k equals 0. This is going to be 1, okay, because for k equals 0, there are no terms in this expansion. K equal 1, I have 1 minus 1 over n times 1. So that makes still 1. K equal 2 gives 1 over 2 factorial, 1 minus 1 over n, 1 minus 2 minus 1. So this gives 1 over n itself. There we go. So here in all this product, I will have only one term when k equals 2. When k equals 3, how many terms will I have? So I will have 1 minus 1 over n, 1 minus 2 over n. Okay, and we can keep going. Every time I will get more and more until k equals n factorial. Here I have 1 minus 1 over n, all the way to 1 minus n minus 1 divided by n. Now, let's pay attention to what we have here. So we have 1 plus 1 plus 1 over 2 factorial times something, 1 over 3 factorial times something, all the way to 1 over n factorial times something. Okay, and I was very technical here writing stuff. Okay, but this stuff actually is a stuff that is something less than 1. So I can also write that, stuff less than 1. And now when we look back to the formula for Sn, we notice that if we remove that stuff, we just ignore it, what we are going to get is something larger, which is the definition of Sn. Okay? This is because the stuff is less than 1 in all the cases. Okay? This is, of course, not very technical. I'm writing stuff because we are explaining the proof from the book. Okay? But you can just make a note saying, well, 1 minus 1 over n, or 1 minus 2 over n, or in general, any of these terms are going to be less than 1. So I can just estimate them by 1 and get something larger. Okay, so what did we get here? What we got here is that Tn is less than Sn. We can say less or equal if we want. And that means that the lim sup, as n tends to infinity of the Tn is less or equal than the lim sup of the Sn. Okay, but the lim sup of the Sn, because Sn converges, we already said that, and we define it as converging to the number e, this is equal to e. Okay. Remember, if there is convergence, the lim sup equals the limit. So that's one thing we have already. The lim sup of Tn less or equal than e. Now, if we are able to show that e is less or equal than the lim inf of the Tn, we are good to go, because we will have proved that the lim sup of the Tn is less or equal than e, less or equal than the lim inf of the Tn. And because the lim inf by definition is less or equal than the lim sup, we have all equalities here. We have that e equals the lim inf equals of the Tn equals the lim sup, and when the lim sup and the lim inf are equal, then that's equal to the limit. Okay, so this is the game plan. Okay, but we need to prove that e is less or equal than the lim inf. Okay, so let's be clear here. The plan is to prove, and then we can do this whole thing I said. Okay, so let's go for it. Now, notice one thing. So let's say, for now, let's say n, let's pick some number m, and let's say that n is bigger than that number n. Okay, so we have Tn, the computation I just did, okay, which is here. I'm going to copy paste it. This Tn, okay, is actually, this is an equality, sorry. This is bigger or equal than if I just cut it off and stop the sum earlier. Instead of going all the way to n, I'm going to stop at m. Okay, so I write here m, okay, f. So here I'm cutting off m minus n terms. Okay, that's the reason why I have an inequality here. Okay, I have less terms. Now, keep m fixed and let me take the lim inf as n tends to infinity. I get that the lim inf of Tn is bigger or equal than this thing, this little monster here, but let's look at it carefully. When n tends to infinity, everything that depends on n, because it's dividing 1 over n, 1 over n, 2 over n, n minus 1 over, actually this is an n. All these are going to vanish, okay? So what I'm going to get is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial all the way to 1 over n factorial. This is because all these terms here that I'm highlighting as n tends to infinity go to 0. Okay. But this here that I got, sorry, this is m, not n. I already took the limit as n tends to infinity, so there must be no n's left. Okay, so once I have this, what I get here is Sm. Okay, that's the definition, is the partial sum. So Sm less or equal than the lim inf of the Tn n to infinity. Let me take the lim inf as m tends to infinity. At this point I can do that, or I could take just the limit itself, because we saw that the series converges, okay? And that is equal to E. So we have proved that E is less or equal than the lim inf of Tn n to infinity. And that was the other half of the result, okay? Remember, I wanted to prove that E was less or equal than the lim inf, because then that makes a sandwich to the, I have the lim sup on the left, the lim inf on the right, and E in the middle. This is a very common technique. If you want to show that something has a limit, show that the lim sup is less or equal than the lim inf. Then they must be equal, okay? Because naturally the other inequality is true. The lim inf is always less or equal than the lim sup. Okay, so if you are able to prove the reversed one, then you are going to have a limit. Okay. Now, some things about the number E that are very interesting. This closes the proof. Now the series 1 over n factorial from 0 to infinity converges very fast. Very fast, as in highlighted very fast. Okay, how do we show that? We can compute the remainder. Okay, what is the difference between a partial sum and the definition of E? And this is going to be all the terms that are beyond the partial sum, right? We have 1 plus 1 plus 1 over 2 factorial plus 1 over n factorial, 1 over n plus 1 factorial, and so on, minus the partial sum, right? So there's a big cancellation here, and I get 1 over n plus 1 factorial plus 1 over n plus 2 factorial, n plus 3 factorial, and so on. This is an infinite series. Okay, but now notice this is n plus 2 times n plus 1 factorial. This is n plus 3, n plus 2, n plus 1 factorial. So I can just factor out the n plus 1 factorial. I get 1 plus 1 divided by n plus 2, 1 divided by n plus 2, n plus 3, and so on. Okay. And now we can make an estimate here. N plus 3, this is bigger than n plus 2, right? So if I put something smaller in the denominator, I will get something larger for an estimate. So this is 1 plus 1 over n plus 2 plus 1 over n plus 2 squared, and so on. But now this is a geometric series, right? So we can just take the sum of the series, 1 divided by 1 minus 1 over n plus 2. Okay. And that's it. Now I'm realizing that actually we can do this even better. So we can take the n plus 2, it's bigger than n plus 1. So I can estimate everything by n plus 1 instead. Okay, so I have a geometric series which instead of n plus 2 has n plus 1. Okay, so then when I sum it up, I get n plus 1. And now it's a little nicer because what I have in the denominator is n plus 1 minus 1 divided by n plus 1. So there is a cancellation, and this is n plus 1 divided by n plus 1 factorial n. Okay, but then I can cancel a little bit more here, and I get 1 divided by n times n factorial. Okay, you see I did this second estimate, the one that we see in green, because the result looks a little nicer. It wouldn't matter. Qualitatively, it would work the same way, but it's nicer written like this. All right, so what did we do? We estimated the error between the number e and the partial sum as being less than n divided by n factorial. And now the factorial is like the fastest growing function that we can plug in here. Okay, notice that the exponential, sorry, the number e is always going to be larger than the partial sums because the sequence is monotone. I wrote s sub s, but I meant s sub n. Okay. Now, for example, how many decimal digits are we going to get if we compute S10? Okay, when we compute S10, we need to know how much 10 times 10 factorial is, but I punched this in the calculator and I got 3.6288 times 10 to the 7. Okay, this is an equality. Okay, there is no approximation here. But if I divide, that means that if I add 10 terms of the partial sum, I'm getting an error less than 10 to the minus 7. Okay, so that's a really good. I think for most engineering purposes, you don't really need more decimals than this. I think you can put a satellite in Mars with this accuracy, but don't take my words for that. Okay. But actually this inequality we have proved is very interesting because it allows to show something that we have been mentioning but not actually proving, shows that E is irrational. Okay, and it follows from this inequality. Let's prove it. So let's keep this on the side. Proof by contradiction. Assume to the contrary that E is a rational number. Okay, we can say right away that E is of the form P divided by Q, okay, with PQ integer numbers. We know they are positive anyway, and Q different from 0. And we can assume this is simplified, but we are not going to use that in the proof. So I will not bother writing that down. Okay, now we can apply this formula, but we apply it for n equal q. Remember, q is a positive integer. Okay, we can assume q is a positive integer. Now, how will it look like? Is q less than 1 over q factorial. And actually, let me move the q factorial. Let me move it here. Okay, we have the same thing. And now let's look carefully at this expression we have, q factorial times e minus sq. My claim is that q factorial e minus sq, this is an integer number. Okay, and that will be a contradiction because there are no integers between 0 and 1. Remember, 1 over q is less than 1. Okay, so let's work on this claim. We get this claim, we get the proof. But it's actually quite straightforward. We need to look at both q factorial e and q factorial sq. Now, the q factorial sq goes first. No, actually, let's do them in order. Q factorial e, this one is an integer because by assumption, e is, let's continue here. By assumption, e is equal to p over q, so we have q minus 1 factorial times p, which is an integer. Okay, now the second one, we have q factorial times 1 plus 1 plus 1 over 2 plus 1 over 3 factorial. I can write the factorials, plus 1 over q factorial. Okay, we can write it expanded. And then we realize that the q factorial here contains 2 factorial, 3 factorial, all of them up to q factorial. So all these products they are all going to be an integer number, okay? Because I can cancel, this will be q times q minus 1 all the way to 4, okay? And so on. So this is an integer number. And then the sum of two integer numbers is an integer number. So we are done here.